So let's talk about why I have this in front of the class on this box. What is this?
Scale.
Okay, it's a scale. How does it work? Sean?
Tells what item weighs more.
Okay, or that they weigh the same,
Oh, yeah.
right? So either they both weigh the same, or one weighs more. Their default, one of them is less. Okay. What do you think this scale represents for an algebra class? In algebra, in a math class, when we look at things that are the same.
Volume.
Does the scale itself represent volume? No, it doesn't represent volume. Okay.
Mass.
Like the weight?
The scale more like literally weighs weight. What does it represent in a math class?
Like an equal?
Yes, right? Both sides are equal, so it represents an equation. Okay, both sides are equal. And I want to take a few minutes to talk about this. I may bring it out every now and then to remind us what an equation is, because we talked about this. This was maybe weeks ago by now. But in previous years, like in the younger math classes, you may have thought of an equal sign in this way: 5 plus 3, right? Do something, get the answer, and equals means I got the answer. Right? Does that sound familiar?
Yes.
Yeah, but equals doesn't mean I've done something. What does equal mean?
They're equivalent.
They're equivalent, and it's true, they are equivalent. Okay? And that's how an algebraist thinks about an equation. This side and this side are equal to each other. It's not that I did something on this side to get this side, it's just that they are equal to each other. Okay? So when we have an equation in algebra, it might look something like, got this, well, let's first look at, got 5 and 5, put them on both sides. What do you think is going to happen?
They're gonna have six.
It's going to be equal, because 5 is equal to 5. Okay. Now I put 1 over here. What's going to happen?
Then the left side's gonna drop.
Okay, so to keep it balanced, I should
Put them on the other side.
put 1 over there. Okay, so far so good. Alright. Now we have this mystery container here. Right? So naturally that side is heavier. So this is how you would use a scale in real life. You would just in there, it's not worth 1, 2, so it must be worth
3.
pop this open and see. There's only 2 inside.
The thing.
The container weighs as much as 1 thing. Yeah. So. Okay. Let's say now that I. So what do we have here? So like somebody could come up and take a closer look if you want to describe it, Alex.
Okay. So the mystery container, and there's 3 there, and so there's 4. There's 9 here. So this must have the mystery container.
I just want you to tell me what you see. Not, I don't want you to like
Well, there's a
figure
container
anything
and
out.
little counters.
Huh?
There's a container and little counters, and they equal each other.
Right, and how many do you see on this side?
10.
Okay, 10. All right, that's all I need for now. Thank you, Alex. So on this side, we have one of those containers that has a hidden number of, or is worth a hidden number of tokens. And on that side as well, we have 3 little things there. On the other side, we have little tokens. Okay. Let's first write an equation to represent what's going on here. So we can translate this physical object to a symbolic equation. Yeah.
X plus 3 equals 10.
Exactly. Okay. Now, we've just gone from a scale to an equation. When you see an equation, I want you to think of it as being balanced on both sides. Okay? And what we do to an equation, whatever happens to the equation, whatever we do to it, what should we always make sure of? Okay?
You want to make sure you keep it balanced, and you do it to each side.
Keep it balanced. And that's why we do the same thing on both sides. When I first started learning algebra, I was in 8th grade as well, and I thought it was really fun. It was like a little puzzle. And I thought of it more as like, oh, there's these rules that we can follow. Like it's a game. And it is kind of like a game, but I didn't understand why we did the same thing to both sides. I mean, it kind of made sense that we would do that, but I didn't quite grasp it. And I don't know if it was ever explained to me. So I like to make a point with my students to explain exactly why we do the same thing to both sides. Okay? If you wanted to leave the scale in such a way that you have the unknown thing on one side and, well, an equivalent amount of little discs on this side so that I would know how much that thing is, how much that weighs. How would I do that? How would I physically do it with these objects? Monica.
You take the 3 tokens off.
I'm going to take, because I want to get x by itself. I want x to be left on one side, and therefore the other side will be, well, it will tell me what x is worth, right? So I want to get rid of all that extra stuff. Let's get rid of that extra stuff.
And then take off from the other side.
Take away the same amount from the other side, so both sides are the same. Now with a scale, we can see that it's the same. We can just kind of mess around with it, make sure that it's equal. I can just take this thing off, right? Hold it in my hand, get a bunch of tokens, drop them on the other side, place the thing by itself on this side, right? That's how a scale works. That's how merchants used to use scales. But with an equation, it's a little harder to do. I can't just pick up this x and then drop a bunch of tokens on this side and then see when it levels off, right? The only way I can be sure that that thing's going to stay the same on both sides is to disturb both sides in exactly the same way. Right? So x plus 3 equals 10, represented as this scale where we took so I take these off of this side, and I take 3 off of this side as well, and now I know that that container must be worth how many? 7. Pretty straightforward. In the equation, how do we represent that exact same process? Johnny?
X equals 7.
What? Like, how do we represent the taking of things from both sides?
You go x plus 3 minus 3.
So we subtract 3 from this side.
And then go 10 minus
We subtract 3 from this side, okay? Because it's a balanced thing, like a scale, and we take the same amount from both sides. Okay? And plus 3 and minus 3 together are 0. So we're left with x plus 0, or just x equals 7. Sean? I know it's almost an overcomplication of a very simple idea. Probably walked in today, all of us knowing that to solve this equation we need to subtract 3 from both sides. That's not the point of what I'm trying to tell you here. The point is that no matter how complicated an equation might get, if our goal, and it oftentimes is, if our goal is to solve this equation for x, then we need to keep those same principles in mind. It goes for every kind of operation. For example, here, I'll just represent it as a picture. Let's say I went over here, and I'll copy this container. And now everything is different, so get rid of all this stuff. Boy, phone should go phone jail. See it right there. So now, I have 2 of these unknown things on one side, and 8 tokens, right? What do these tokens represent, like in math? Algebra, Sean?
1.
1. A 1 unit, right? 1 number. So, what would you do to figure out how, like, you're not allowed to just take them and then put tokens on one side until it comes out the same. You just want to do operations that are going to keep both sides the same. So what would you do to this scale? Okay. You might be able to see pretty naturally what x must be worth, but I want you to justify that using, doing things to both sides. Blake?
Would it be 2x equals 10, or 4, or 8?
If we were to write an equation, yes, it would be 2x equals 8. What I'm asking though is, what would you do to both sides of the scale, okay, to make sure that it stays the same on both sides? What would you physically do if this was right in front of you? What would you do to both sides so you could be sure that both sides must stay the same?
Well, I don't know if it's right, but take one of those green containers.
Okay, there's 2 green containers. You're going to take one of the green containers.
Take it out.
Okay.
And then take 4 of those,
Now, why 4 of these?
because it equals 1 container, because it's equal.
Now, okay, justify that a little bit more. How do you know that 4 of those is worth 1 of those?
Well, you're taking off half of the, half
Mm-hmm.
off that side
Mhm.
and like, half of, it's kind of, half of that side equals half of that side.
Yeah, if this side equals that side, then half of this side should equal half of this side, right?
Yeah, so
Must
you're
make
gonna take
sense.
off half.
So we're gonna take half of, that's all I was looking for, half of both sides. Okay? So half of that side must be the same as half of that side. Now we're looking at a single unknown quantity is equal to 4 ones. 4. And so what does that look like in an equation? Yeah.
4 from each side, well,
You said it yourself. What word did you use to describe why you were
take
sure?
off half,
Half. How do I take half of this?
you divide it by 2.
Half. There we go. Half. 110. Right? You take half of 2 x's, half of 8, and I get x is 4. So far so good?
Yeah.
Be basic, right? Well, that's where we should start, is with the basics. Right. So this, it can be a little cumbersome to use, so I try to make the point strongly here at the beginning. The reason this is, well, the purpose of this symbol is to say that both sides are the same. And we must keep both sides the same. And that'll continue, like I said, for anything that we do to both sides. If I find half of this side, I need to take half of this side. If I find a third of this side, I need to find a third of this side. If I find the square root of this side, if for some reason that seems advantageous, if I find the square root of this side, I should find the square root of this side. Okay? Equivalent little pieces of equivalent things must be equivalent to each other. if you look around at these green pieces of paper, they essentially say things like that. Here's, well, there's a better one that right back there. Common notion number 2 back there by the office supplies. If equals are added to equals, then the wholes are equal. Right? Does that make sense? You think about a scale like this. If equals are added to equals, so if I add the same thing to both of these sides, they're already equal. I'm adding the same thing to both sides. The result must be 2 things that are equal to each other. So if we take the square root of one thing, we're going to take the square root of both sides. If we square both sides, we'll square one side. We're going to square the other side. If we multiply one side by x, we're going to multiply the other side by x, which becomes a very difficult thing to show. Like, how would I multiply this container by itself? You see what I'm saying? Sometimes we can't. We use these analogies. We can't really show in real life what we can do with symbols. Okay. But if we multiply one side by x, we multiply the other side by x, and sometimes that's the thing that you want to do. Sometimes that is what makes the equation easier to isolate x. And when you get into calculus, you take the derivative of both sides, you take the integral of both sides of an equation. They're both the same, so their derivatives must be the same, or their integrals must be the same. Okay, so let's see how you do with some basic equations. Okay, like 5 minus 3.2 equals 6. S. No, my S is notoriously like 5s. P plus 2/3 equals. Let's see if we can all solve all 3 of those equations on our own. All right, so x plus 5 equals 17. How do we solve this equation? How do we figure out what x is? Minus 5. Okay. So I'm going to write it like this. 17 minus 5, 12. So x plus 5 minus 5 equals 12. So we know that
X equals 12.
x has to be 12 because these things cancel each other out, right? Might as well be a 0, which we usually do right. We cancel those out and write them as a 0. Really, this is what we're doing. We're trying to, as we work up in complexity of these equations, we're trying to get it so that we have just x, or x plus nothing else, or x times 1, right? That's the same as x. Or x divided by 1. So why do we subtract 5 from both sides? Yeah?
To even out the problem.
Even out the problem, how can we do it to both sides?
Because if you don't do it to one side won't be the same as the other.
So if you only do it to one side and not the other, then they'll be all lopsided,
Yeah.
right? Just like that scale.
Yeah.
Here's the answer to that question as I would put it, because both sides are equal and they must remain equal. If they don't remain equal, then we'll never know what x is. We'll be lost in space. We'll never know if we mess it up like that. We'll have to work our way back to the last thing we know is correct, and then proceed from there. Cadence, you have something to add? Okay. What would we do in this case? We have x, and if you take 3.2 away from x, you would get 5.16. So
you add 3.2.
Add 3.2. So negative 3.2 plus 3.2 is 0.
X equals 8.36.
Agreed. 8.36. This last one, Josie?
So first of all, you would subtract 2/3
First of
on
all.
each side.
Okay.
To do that, you have to find common denominators.
Good. In order to do this thing we're trying to do on this other side, we need a common denominator. What is that common denominator?
I chose 12.
12. I like 12. So we're going to take, how many 12s is this?
9.
9 12s, multiply both by 3, yeah?
And then the other one's 8.
8 12, so we're winds up with
1/12.
1/12. So, here's something I want you to do. Over the weekend, I want you to come up with one equation that involves at least one variable. It could have more variables. Let me give you an example. If I look across the parking lot there, I see a house, right? House has a roof, right? And with the siding there, the vinyl siding, it makes a triangle. Okay? So I could say this is x, y, and this is z, and what equation can I write? Yeah?
X plus y plus z equals 180.
Exactly. Here's another one. Let's say x minus s equals d. It does look like a shot.
It really does.
So this equation represents me getting on the scale with my son and weighing how much we weigh together. Me, Mr. Stewart, getting on the scale, subtracting my weight from that weight and getting my son's weight, Declan's weight. Who's incidentally, his birthday is today, so happy birthday to him. You have a great day, everybody, a great weekend.
So we can come up with an equation.
Any equation just like that, x plus y plus z equals 180, or this thing with the scale. Okay, don't just recreate exactly what I had. Or maybe you go to the store, something with money, right? Definitely opportunities for equations there.